Uh, it's always a great pleasure to be back here in South Africa. I was born here, have lived a little while in the UK, and I'm now in the United States, but I can tell you that my emotional soul is stuck firmly in African soil. So it's always really great to be back, and a special word of thanks to Dr. Sibisi for this invitation to be here with you today. And I wanted to talk to you about energy storage, maybe from a slightly personal perspective. And I really enjoy the title and the theme of this meeting, Ideas That Work, because I'm going to tell you a little bit about ideas that worked and still working, and then also just talk a little bit about the future and the challenges that lie ahead. So just some acknowledgements. And I'm just acknowledging the institutions that have supported me through my career. Obviously, CSIR, I spent 20 years here. We were very well funded by Anglo-American and De Beers in generating some new intellectual property and getting it out there in the market. And Technifin, or Sitecore, South African Inventions Development Company, for supplying the funding to actually get these patents filed worldwide. I had a stint at Oxford University, and that was a real turning point in my career, and for the last 20 years or so been supported by the US Department of Energy, the Office of Energy Efficiency and Renewable Energies, the Vehicle Technologies Program. Our major mission is electric vehicles. They're the applied side of the Department of Energy, and we're also getting funding from the Office of Science, Basic Energy Sciences, to do some of the fundamental work to prop up the applied and to serve the applied programs. We're incredibly strong at Argonne at the moment. We've grown the program. We've got 3 different departments, 1 in the applied side, 2 from basic energy sciences, and probably all in all, if you take those folks that work with us across the country, we're about 300, 350 strong in terms of US battery R&D. I want to start off just with a couple of comments about global stress, and this is, I think, becoming more and more well known to everybody. The population growth is burgeoning, and that means that we're a smaller world, we're a much more connected world, but there are these unsustainable tensions that are developing as mankind strives for equality and a share of natural resources. And you see this very clearly, I think, in all the movement of the population that's occurring in Europe. And of course, the rise and spread of lethal diseases is still, at times, like Ebola, a major crisis. But just as important is the harnessing and storage of energy. We've got to lessen our dependence on fossil fuels. And as you very well know in this country, minimize the interruption of power supply that plagues developing countries such as South Africa and India and such like. And got to find a way of providing a means for slowing CO2 emissions and global warming. And I think many of you have seen slides and data like this. This comes out of Hawaii, and just showing the increase in the CO2 levels. We are approaching 400 ppm. That is, you can just imagine that over the past 150 years or so, just the amount of fuel that's actually just been burnt and polluting the atmosphere. I mean, there's billions and billions of tons per year. So there is this threat, not only to the planet, but mankind as well. So these are tracks of world energy consumption from 1820 through to 2000. And in 2010, and nothing much has changed, 90% of the energy that we use comes from coal, oil, and natural gas, all carbon-emitting materials. And down below is the world population, also from 1820 to today. All of these are on the same trajectory: world energy consumption, world population, and CO2 emissions. It's a very, very serious problem. So in my opinion, there's really no time to waste. It took it took millions and millions of years to produce the oil that we use, and it's taken us about 150 years to deplete much of the fossil fuel reserves. The first oil production facilities went up about 150 years ago. About the same time, the batteries were being invented. So, but this increase again in CO2 emissions is just absolutely unsustainable. In the United States, fuel is unbelievably cheap. We pay at about $2.50 a gallon. So that's roughly about 60 cents a litre. So in terms of fuel, very inexpensive. But despite that, I believe that this drop in the oil price to less than $50 a barrel is immaterial in terms of the problems that mankind faces. So again, urgent need to develop technologies to harness and store energy to electrify this planet. And again, significant progress has been made in battery technology in the past 150 years, and put us at a stage where we can start to address the issues that confront us today. Well, energy transformation takes time. Again, going back about 150 years, wood was the primary source of fuel, and that led to coal, and both of those have waned over the years. Hydro, you can see in the blue, has maintained its share, hasn't changed much. This is oil, and this is natural gas, still supplying most of the energy requirements for today. Nuclear is relatively low, but renewables have just started to enter this graph, and the hope is, I think, in many, many minds, is that this is going to start increasing in terms of its impact on energy supply. So it's a question about electrifying the planet, and we know very well that battery-powered communication is now connecting the world very, very rapidly. The introduction of, and indeed, lithium-ion batteries, which are the power source, and the development of the cell phone, it goes beyond one-on-one communication. It goes into education, it goes into health, it goes into family cohesion, it goes into wildlife preservation. I mean, this communication has revolutionized the way that we live. Of course, everybody's now looking at electric vehicles as the potential way to go in terms of transportation, and the electrical grid as a storage for the electrical grid, and renewable energy sources are going to play an increasingly important role in that regard. And of course, batteries in the grid are going to become inextricably linked. So this is what the situation was in the mid-1970s, the first oil crisis in the Middle East. And this was at the time that I joined CSIR. And the only two rechargeable battery systems of any worth at the time were lead acid and nickel cadmium. Nickel iron and nickel zinc were a little bit under development at the time. But in 1967, there was a revolutionary breakthrough, this discovery of beta alumina, which is a fast sodium ion conductor, which initiated international research on high temperature systems. And the one main system that was in vogue in those days, still under development, was sodium sulfur, operating at about 350 degrees. But at that temperature, you have molten sodium and molten sulfur separated by this very thin beta alumina ceramic, and very reactive if the beta alumina ceramic fractured, a very violent reaction. So there are a lot of safety aspects of sodium sulfur, and it hasn't found its way into transportation, but it still is there in terms of energy storage. The other system that I want to mention is lithium-ion disulfide in the mid-1970s, making use of a lithium aluminium alloy, which is solid at high temperatures, and the solid iron disulfide cathode. So these were the two systems that were being developed in the mid-1970s. So at that time, I joined the CSIR from Cape Town, and in 1974, Johan Kutzer initiated a program on solid electrolytes and contract research from 1978 onwards on these high temperature type battery systems. And the realization and the motivation for doing this work was that electric vehicles really were considered to have the potential for large-scale market growth, at least by the turn of the century, by 2000. So De Beers and Anglo-American showed interest, and they went away from their normal mining R&D programs and started taking an interest in energy storage. And they were a great funding source for us. So the small and focused and innovative R&D team work was created, and there was heavy involvement from senior management from CSIR, De Beers, and Anglo-American. We had monthly meetings, engineers, scientists, and of course patent attorneys to make sure that any new ideas were protected. So the two systems were based on, lithium, aluminium, iron disulfide, the system at Argonne, and the sodium sulfur system, which was under development at Chloride, Silent Power, and British Rail in the UK. This is a shot from, I guess, maybe the early 80s, or maybe late 1970s. This is Johann Kutzer. Some of you might remember him. Real lateral thinker, and just an inspiration to work with. I just joined. This is Jeff Gaffner, who was head of the crystallography department, Gert Krier, who some of you would know as well, and then the battery team in the background. And this was the strategic thinking that happened in the chain of events. Johann thought that, well, safety was one of the big issues of sodium sulfur, so he had the idea of taking an aluminosilicate zeolite, pumping the water out of the zeolite and replacing it with sulfur, and so immobilized the sulfur, put it into the solid state instead of having it in the liquid state. We worked on that for a couple of years, but there was too much dead weight in the zeolite, which ultimately proved it not very effective. So in 1979, about a year later, we redirected the project to argon's high-temperature lithium configuration, but we replaced the lithium iron sulfide with lithium chloride to get away again from corrosion problems of the sulfur. So the reaction, the two reactions that you can see are given up in these reactions right here, and this is what we looked at, the reduction of iron chloride to give us lithium chloride 9. But there were major solubility problems in the high temperature molten salt electrolyte that we were using. So that didn't really work either, and Anglo-American were beginning to get a little bit frustrated with us, saying that, well, you're chopping and changing your minds, you better find something if you want us to continue with the program. So maybe it's serendipitously and with a bit of luck, again, Johann Kutzer discovered this molten salt sodium aluminum chloride, which melted at 150 degrees C, and his idea now was really great. I mean, he combined the concept of sodium, the sodium sulfur system, and the argon cathode technology. And his idea was to use the beta alumina ceramic, but this time with sodium aluminum chloride as a liquid electrolyte to make contact with the solid cathode, which you see on the right-hand side, salt and iron. And the electrochemical reaction is really, after you charged it up, was just on discharge, the reaction of sodium and iron chloride to form sodium chloride 9. And so Zebra technology, this is the code name that we used in those days because science was politically disenfranchised, if I may use that word. We had to have help in terms of getting the sodium beta alumina technology into South Africa, and we had to do that under wraps. So what is beautiful about the Zebra technology is that you could actually load the cells in the discharge state. You just took sodium chloride and iron powder and mixed them up and put them in the right configuration, heated it up, and then charged the cell and electrochemically pulled the sodium out of the salt and created iron chloride. And it worked really well, with, particularly with nickel instead of iron. But another beautiful thing about the reaction was that if the beta alumina ceramic fractured, the sodium would just reduce the sodium aluminum chloride, produce aluminum metal, and the system would just short out and prevent any violent reaction. So in 1981, CSIR, De Beers, Anglo-American intensified their efforts in this technology. They expanded the team and they brought in overseas expertise, which is critical. And I've always had this notion that when you start running into trouble in science and technology, you go to the people that are really going to be able to help you. And this is absolutely true from a technological standpoint as well. In 1985, the team teamed up with Daimler-Benz to develop and implement Zebra batteries. In 1992, it was demonstrated on the Autobahns in A-class Mercedes cars and used in buses at the Barcelona Olympics. And the tragedy was that in 1999, there just wasn't this infrastructure in place worldwide for electric vehicles. The time scale was far too short. So both Anglo-American and Daimler-Benz walked away from this multi-million-dollar project. They sold, I believe, for about $20 million. They just walked away. A great tragedy. But the good news was that the technology is still alive. They sold out, and Zebra batteries are still being produced in Europe now for EVs, and in the United States for energy storage, stationary storage, and electrical backup systems for communications in particular. But there was a big spin-off to this technology. We also looked at replacing the iron sulfide with iron oxide, which was less corrosive as well, and we looked in particular at the spinel, Fe3O4. But in 1981, despite the fact that the cell really worked well, Anglo-American gave it the thumbs down. The discharge voltage was far too low for it to be of any interest. So the idea was taken to Oxford in 1981 and to explore the possibility of using these spinels such as Fe3O4 in a lithium cell. And a big discovery was made there, that the stability of what I call the Fe2O4 spinel framework, that's without one of the ions, provided a three-dimensional space for lithium-ion insertion. And that immediately had implications for lithium spinels, such as lithium manganese oxide, and used that as an intercalation electrode in room temperature lithium cells. And the idea came from CSIR, and so the spinel patent was filed in CSIR's name. But you must remember, this was 1981. It was still 10 years away from the introduction of lithium-ion technology. In 1983, De Beers and Anglo gave the thumbs down on even despite that breakthrough, because they hadn't realized the implications of what was to follow. And they opted to stick, and I think quite rationally so, with the high-temperature sodium metal chloride system, which was really showing great promise. And the lithium project was returned to CSIR. So between 1981 and 1994, CSIR developed and licensed its intellectual property portfolio on spinel and other lithium-ion battery materials. So in a way, CSIR research in the 70s and 80s was way ahead of its time. So the take-home messages from that period for me, which is about a 20-year period, was, new ideas really do take time to germinate, develop, and grow. And that really is the rationale behind and the impetus for and the driving force for getting scientific research well supported. But you've also got to know when to persevere, redirect, or withdraw. We hit the wall several times in some of these technologies which weren't going to work, and they were de-emphasized in terms of the scientific programs. So this is the scenario today in terms of rechargeable batteries, and you still see lead acid and the nickel-cadmium system, which is being replaced by nickel metal hydride, which was introduced particularly in the Prius in the early 1990s as the power source for the electric motor. And here you see sodium sulfur, which has been commercialized. The lithium-ion disulfide program from Argon has disappeared. It worked as a primary system, but not a rechargeable. But here you see CSIR's sodium metal chloride, which is still operational. Of course, lithium-ion has been the big winner. Introduced in 1991, and I'll say a little bit more about that in a few moments. And then there are these futuristic systems based on lithium metal anodes, very, very difficult technologies to manage. The ultimate one would be lithium oxygen, where you're getting energy densities which are far in excess of those that you can expect from any of the other systems. So lithium-ion systems still today offer the best near-term opportunities for improvement. And today it's just amazing, 25 years from its inception in 1991, lithium-ion technology or batteries commands about 40% of the market, as does lead acid, and there are a few other systems that make up the remaining 20%. So the impact of lithium-ion batteries has been enormous because you can actually tailor the cell potential and you can use it in diverse applications. Consumer electronics was the big driver in the 1990s. What I call the lithium economy driver is going to be found in transportation, and you see that happening now. Hybrid electric vehicles and plug-in hybrid electric vehicles really the way to go for the near term, and although all electric vehicles, that's without any backup in terms of a gasoline engine, a little bit further down the track, but you still see them coming in local communities. Stationary energy storage, I mean, it's going to be there as a backup supply for communications and as a potential feed into the electrical grid and to help offset the peak periods where extra electricity is required. It's ubiquitous. It's found in medical devices, aerospace, defense, power tools, and toys. And I like to show this slide of or the numbers of the number of publications. If you put lithium battery in as the keywords, in 1980 there were 34 publications. In 1990, when we were working here at the CSIR, we probably contributed mainly to a lot of the publications that were being issued in those days. But in 2000, after Sony had introduced the first product, you see this massive jump from 36 to 749, and it's grown ever since, and about 8,000 published publications appearing each year now. So again, the lithium-ion batteries introduced by Sony in 1991, and the principle is shown above. The prototype was lithium cobalt oxide cathode, which contains lithium in these layers within a crystallographic structure, and these are cobalt oxide layers. This is graphite, which is the carbon anode, and during the electrochemical operation, you electrochemically extract the lithium from the lithium cobalt oxide and insert it into the anode during the charging process, and then the reverse process happens during discharge. Highly energetic systems. This is about 4 volts. The electrolytes are based on organic solvents, which are flammable. So inherently unsafe technology, and individual cells, every single cell that you have in your laptop computer or cell phone is protected by fairly sophisticated electronic circuitry. And you can imagine, though, that as you cycle this lithium during charge and discharge, the materials start to get a bit tired and they start to break up. So cycle life and the stability of these materials is vitally important for the lifetime of the batteries. And when it comes to transportation, you want your battery to last 10 to 15 years. So electrode and electrolyte materials really do dictate the performance and safety of lithium-ion batteries. So these are the 3 main cathode materials, and I just want to focus on them. There are lots of components in lithium-ion batteries, but the cathode material is really the one that gives you the potential, the voltage. And there are 3 main systems. There's the lithium cobalt oxide, LAD, 2-dimensional space for lithium to go in and out. You have the CSIR spinel, which is a 3-dimensional conductor for lithium ion. It's a high power electrode, and you have olivine, which has 1-dimensional channels for lithium ion transport. But the one thing that I just want you to remember is these values of capacity. The capacity of an electrode is based on the number of electrons that can be transferred per electrochemically active transition metal ion. And these values range from about 100 to 150 milliamp hours per gram. Just remember that, because the energy of a cell is the product of voltage times capacity. So you want the voltage to be high. There's nothing much that you can do about that unless you want a lower energy cell. But something that one might be able to do is to increase the capacity of the electrode. So a couple of years after I got to Argonne, we were working on trying to increase the capacity of lithium cobalt oxide, for example. And the idea that we used was to take a structurally compatible layered material such as Li2MNO3 and embed that at an atomic level to give it some extra stability, and with the hope that you could take a little bit more lithium out and put it back in again during charge and discharge. And it's worked incredibly well. I want to put up this shot, and this is a paper that Rita Rousseau here at the CSIR was responsible for. We started looking at this compound Li2O3, but our motivation there was to make a layered manganese oxide, a new manganese oxide compound that hadn't been made before, like lithium cobalt oxide, because to have the two-dimensional interstitial space. And we were fairly successful in doing that by leaching out lithium and oxygen, dissolving lithium effectively from Li2O3 to give you a layered compound. It was a 3-volt lithium cell, and we didn't do much further on that. But that material really contained some of the clues which were going to lead to further advances that we were able to make at Argonne National Labs. And this might seem quite complex, but I hope it's not all that difficult to understand. But here's lithium, the composition of lithium cobalt oxide, for example. And if you take lithium out, you go up, you change the composition towards a totally depleted layered compound. But in practice, you can take about 50% out, and you can get 140 milliamp hours per gram when you charge to 4.3 volts. If you stabilize with a little bit, 5 to 10% of Li2O3, you go up the dotted line, the red dotted line, and you get about 160 milliamp hours per gram. And that's the Argonne technology, and it's what we call Generation 1, and it's been patented and licensed worldwide. But if you increase the Li2O3 content and add just dead matter, the capacity obviously decreases. But it was discovered that if you go to these high potentials, 4.4 volts, you can start to strip lithium and oxygen out of the Li2O3 and drive the composition back up towards the apex of the tie line. You can come back and you can get a huge amount of capacity. We call this Gen 2, but you have to go up to about 4.6 volts, at least on the initial charge. And there's a huge amount of work being done internationally to optimize the system. So that technology, as I say, was it's one of the success stories that's come out at Argonne, and Argonne's capitalized this. It's ideas that work. This is the theme of this conference. An idea that works talks about success. I mean, this was an idea that worked, and there was a lot of success that came out of it, and it's actually given Argonne a lot of visibility. It's brought in extra money in terms of funding and also in terms of its royalty income. So if it's the importance of being able to recognize ideas that are going to be able to work, and also to protect them with intellectual property. It's a very expensive game, but I always feel if there's something in your gut that says there's potentially something in it, try and get that support to at least to get some protection, at least in the United States and back at home where you are. So by 2002, all these efforts like Zebra and General Electric to get electric vehicles into the marketplace really weren't very, very successful. There was a mandate in California. The California Air Resources Board had a stipulation that within 10 years, 10% of all vehicles in California had to be zero-emission vehicles. And so General Motors worked on this EV1. It was a hugely unprofitable program, only 800 vehicles leased over 4 years at a cost of $4 billion. And they just walked away like Daimler-Benz and Anglo-American did at exactly the same time. The battery technology at the time was just not simply good enough to meet market demands, and an inadequate infrastructure to sustain electric vehicle transportations. And that infrastructure is still inadequate today, but things are happening in the United States, and particularly thanks to Elon Musk and his developments at Tesla. But, you know, to the credit of General Motors in particular, and also the Japanese and the Prius, I mean, there was a recommitment to electric vehicles very, very, very soon after this. In In 1922, it was the end of the first generation of electric vehicles that were powered by lead-acid batteries. People like Edison and was very enthusiastic about it, but it didn't really go anywhere. So that phased out in 1922. By the turn of the 20th century, both the EV1 and the Zebra battery, in terms of transportation, had disappeared out the window as well. But the Prius came in I think, the late 1990s, early 2000s. The Chevy Volt, and this is another GM product that replaced the EV1, going a little bit slowly. It can do about 40 miles to the gallon, but it has a backup petrol tank to take you an extra 200 miles if you need it. But a great commuter vehicle. The Nissan Leaf, of course, Ford Focus, Honda Insight, BMW, and Tesla, and so on, many more. So, just in summary, battery technology has made these dramatic improvements since the inception of the voltaic pile 200 years ago. No doubt that further advances are needed to lessen the consumption of fossil fuels and reduce global warming. No doubt also the growth of lithium-ion batteries has been astronomical, 40% now, and because you can tailor the potential of the batteries, you can design a particular battery for a particular device, and it's become a strategic technology for many, many countries. As you saw, significant progress has been made in introducing lithium-ion batteries in vehicles, and no doubt lithium-ion batteries are also destined to play a major role in grid storage. But at the same time, I think that there's an urgent need, if you're going to use batteries for renewable energy supply, again, to get away from any form of CO2 emission and using coal, for example, or oil as the supply. After the failure of EV1 and the success of the Prius, I believe that we have seen the introduction of this new advanced technologies that are going to push electric transportation forward. So just finally, some opportunities for South Africa. Beneficiation of mineral resources, and you heard about that this morning from the Minister of Science and Technology and also Cyril Ramaphosa. South Africa is, I think, the largest producer of manganese. It's got nickel, aluminium, titanium. You heard titanium mentioned a couple of times as well. Titanium is becoming a bigger player in lithium-ion batteries. And cobalt and lithium itself to a slightly lesser extent. You just don't have the brines of lithium salts, which are the cheapest way to extract lithium and convert that into metallic lithium and lithium products for the lithium-ion industry. And of course, the exploitation of renewable energy sources in this country, solar and wind and energy storage, are going to be vital to lessen the load on the grid in South Africa. The potential market for the grid and renewables in developing countries is absolutely huge. And it was really nice to hear the Minister of Science and Technology saying that South Africa is in the top 10 that is pushing renewable technologies today. And just a final note, for those of you that don't know, is that Argon is currently in consultation with the Department of Science and Technology, CSIR, the University of Limpopo, the University of the Western Cape, also with the South African Consulate in Chicago and the US Embassy in Pretoria that I visited on Monday. We're all there. This interaction with South Africa has been going on for about 2 or 3 years. It's been a little bit slow to begin with, but we're trying to encourage these developments, and if there's anything that we can do to help South Africa in this regard, we'd be delighted to do so. So thank you very much for your attention.